Okay, so at the end of the previous lecture, unfortunately the semester seems to be growing into one of these semesters that we have a lecture and then a lecture is cancelled and so on. We will see how it works out in the end. So at the end of the previous lecture, we had the case of one-dimensional lattice, which has two atoms in its primitive unit cell. So something like this. This distance depicted by D, and this distance by A, and after some mathematics and assuming that K is much smaller than the maximum K pi over A, we got that we have two solutions. And please remember that K is the constant between within and G in between. Gives us twiddle just so we'll separate it in K, which is a wave vector, and large K and G, which are the spring constants. And towards the end I asked the following question. Can take K equal to G? And then basically we can even take D equal A divided by 2. D doesn't come into the solution at all. And then we have exactly the previous one-dimensional with one atom per unit cell. So how come here I have two solutions? And there I had one solution. Here I have two branches, an acoustical branch, which I call acoustical for the simple reason that omega behaves like proportional to K, and one that's K independent. I asked, naming it as a primitive unit cell with 2 or 1 is my prerogative. It has nothing to do with physics. So how come I get two distinct solutions just by naming it in a different way? I asked you to think about it a bit. Anyone has an idea? Okay. Because lectures are good and it's nice to follow the mathematics, but the purpose of lectures is to give you some understanding. And these are the type of questions that actually move you towards understanding, so it's good to give them some consideration. At the end of the day, in 10 or 15 years, no one will remember anything of what appears here on the blackboard, but perhaps someone will retain some of the logic behind what we did here. So the question is simple. How come just by giving a different notation I got a different physical answer? Which cannot be. Okay, the first step is indeed to internalize that it can't be. This cannot be different than the solutions that we gave for a one-dimensional system. Okay, so nevertheless, it's not the same solution. And I will now argue that it is the same solution. Why? Actually, when I did this definition, I missed something. What did I miss? What was the size of the unit cell in the one-dimensional, simple one atom per unit cell? A. What is the distance here after I claim that k is equal to g, d is
A divided by 2.
A divided by 2. So here, okay? The maximal k here is pi over 2a, not pi over a. So if I take the solution for one-dimensional that I did in the previous lecture for the simple case, and I'll just copy it. Okay, so that was my solution. And now, actually, I cannot extend the solution beyond right? So what do I do with this part? It's already not within the allowed k values. I can always move them by g, by the reciprocal vector, into the allowed region. So this part is copied into here. This part copied into here. Okay, take a moment and think about it. Because this is a crucial point. From this, all the behavior of electrons within a lattice and all our further study of phonons will come out of this behavior. What does it actually tell me?
Certain values of
K always in a lattice is always up to movement of the reciprocal lattice vector. Right? It's meaningless otherwise. Right? If you think, if I wouldn't have cut this here for the simple one-dimensional single atom per lattice lattice unit, okay? And I would continue to draw the solution, right? What would I get?
this keeps drawing.
And so on and so forth. Just take the equation that we obtained, which is and insert into k here a value, let's say, of 2 pi over a. Okay, you would get 0. Sinus of pi is 0. You would put in 4 pi over a, 6 pi over a, so on and so forth. All of them will give you 0. So, we said in the previous lecture, it's meaningless to keep all these oscillations because they don't give any additional information. Move them by 2 pi over a to here, move this by 2 pi over a to here, and you're getting the same solution. Therefore, any k up to is the same solution. And therefore, you never bother to write them down. But in this case, the case indicated by red, because we decided that we have 2 atoms per unit site, per unit cell, the effective A here is actually halved, because the distance between 2 identical points is A over 2. Therefore, this line is mapped here, and this line is mapped here. Now, if you do this translation, you have here doubling of the solution. You can't throw out this part of the solution because it's not identical to this part of the solution. So we have 2 branches. So either we could have solved it in this way by paying attention to this, or looking here and we got automatically 2 branches. So this branch is actually the behavior for large case close to pi over A in the previous solution. So, what is my conclusion from all this story? Let's assume I had 3 atoms per unit cell. What is the behavior I'm expecting here?
So the maximum K is pi over 3A?
Mm-hmm. So you cut it to 3 pieces.
Mm-hmm. Wait, but then, we can't, what, the 2 branches, each one gets cut in 2?
No, this red line doesn't exist
the red line doesn't
anymore,
exist.
right?
So what do we do? So it's still just 2 branches?
If you cut something at 2 points, how many?
There are 3 branches.
You have 3 branches. The guy here doesn't essentially change.
Mm-hmm.
So, for let's call it, looking for a number, let's call it n atoms per unit cell. Okay, so we'll have always one acoustic branch. Why? Because the segment around 0 will always start with linear behavior. Why do I call it optical branches? Because even for k going to 0, these branches will start with some finite omega.
What? It's 0.
Hmm?
Yeah. Well, the branches, like at 0, just... Right.
Let's try to find here another color. I'm going now cutting it to 3. Okay? So pi over 3, 2 pi a. So this guy remains in place. Okay? This guy, I move it,
Fold it
into here. And this, and the guy from here comes in here. And this guy will be folded into here, and this guy will be folded into here. Although they are not the same, exactly the same dispersion of omega as function of k, they have one important property in common with all these branches, that they don't start at k equal
0.
At k equals 0 with a dependence on k. They end up with a finite value of omega. Therefore, I call them optical branches. Optical means I have a weak dependence for small k. Okay, now you can come and tell me, look, here you took only a very special case. K equal G, D equal A over 2. What happens, let's say, if K is not exactly G? Okay, so I'll first give a qualitative answer and then maybe we'll do something more quantitative. So I'll erase this part, just I don't want to overburden this. Okay, I'm looking on this is for exactly the same case that we considered in the previous study, that K is equal G. Okay, but what happens if K is not equal G? We'll do the explicit calculation, but I want you to have a mental picture of the behavior before. We'll open a bit of a gap in the solutions, but essentially not much will change. Especially not in the vicinity of k equals 0. Now, these are words. We have to translate it into mathematics, but I just want you to have a mental picture of what's going on here. So let's say doing a perturbation in order to see this opening of this gap, where k is almost equal k0, and so is g, but they're distinct. One is plus delta, the other one is minus delta. So if I write down the equations that we wrote in the previous lecture for the dispersion relation, so I replace k with k0 plus delta and g with k0 minus delta. So far, nothing beyond boring algebra. forgot square root here. So add it, please. Okay, by construction delta over k0 is small, otherwise I could keep the previous notation. Again, just pulling out 1 plus cosinus k a outside. Now, I then remembering something of the trigonometries that we have been playing with in 11th grade. No one remembers anything, but still tangent square. And I'll leave you check at home that putting in a small del, first compare with delta equals 0. You should go back to the previous solution. And for a finite solution, C, just plot that the solutions give you this behavior. Okay, so what do we know until now? Well, we know, first of all, that if you have a one-dimensional lattice with one atom per unit cell, you have one acoustic mode. If you have more than one, let's say n atoms per unit cell, you have one acoustic mode and n minus one optical modes, and optical in the meaning that when k goes to 0, omega doesn't go to 0. And now the question naturally comes, what happens if you have a two-dimensional, three-dimensional lattice? If we want to expand our question, what happens when we have a d-dimensional lattice with n atoms per unit cell?
So you multiply the branches by the dimension?
Correct. So we expect, and we'll show it explicitly, that for 3 dimensions, let's start from the simple case, 3 dimension and 1 atom per unit cell will have 3 acoustical modes. Intuitively, it seems reasonable. We can have propagation in each direction, and why should it be anything else than an acoustical wave? It should be similar in all dimensions. we have m atoms, so we'll have 3 acoustical waves and 3 times n minus 1 optical modes. Okay, let's at least show the part with 1 atom per lattice cell for 3-dimensional system. Should we finish with this? Left the cozy world of 1-dimensional systems, and I'm looking now on a 3-dimensional system. Actually, I would say just before that one word. What happens in the case where we don't have a lattice?
We have to try to define a lattice, right? Just group things together till we have one.
Well, but we don't have a lattice.
What do we have?
Just a random arrangement of atoms.
Yes.
No, solid. You want to meet such a solid?
Well, we can like just set points of the lattice just in space. Then the atoms, then like they have some kind of potential, but the distance from it.
Okay. Let's take to the limit what we have learned. Okay. What will be a unit cell of a disordered lattice, or a lattice that has no repetition?
Some random volume.
The system itself. Exactly. Just will have a size of the size of the system, right?
So just
It seems stupid, but from a mathematical definition, yes.
Okay.
You wanted to say something? Okay. What have we learned actually? That in that case, and I'm pushing our definition to the limits, I know, but still it tells us something. I'll get one acoustical wave, and in principle n-1 or close to infinity number of optical modes, meaning I'll have a very small number of waves that propagate in the system. Most of them will be local fluctuations that don't carry energy far on, because that's an acoustical wave. You do something here and something happens far away.
And because there is only one unit cell, nothing can propagate?
And that's the answer. In disordered systems, at least one-dimensional, one can prove mathematically, I won't go into the proof, nothing propagates. Okay, so if you ever wondered what do you have for acoustical lining? When you put an acoustical lining of a room or something like that, how does it look inside?
Disordered.
Exactly. You'll open it and you'll see disordered, something like wool, like a lot of fibers in all kinds of directions, because that's what it's intended to do. To avoid reflection, just to absorb the sound, and not let it propagate. And to avoid propagation, the best way to do it is either to reflect, but that's not what you want. You don't want to get back all the sound. You want something that will absorb it and do some small local fluctuations, vibrations, but not transmit it and not return it.
What about the one acoustical wave you got?
That's a very limited, small amount of the energy will be transmitted. So I didn't do the mathematics, but this is a correct conclusion out of what we have learned. Okay, so now we are going to the three-dimensional case. And to keep it simple, so this already should be ingrained in you. I start by writing the harmonical potential. So we have written it down in one of the previous lectures, but let's refresh our intuition what it actually tells me. This, you remember, is just a derivative of mu and a derivative of nu, where mu and nu are x, y, z.
Sorry, isn't it supposed to be another constant, like mu, nu, and something for x, y, and z?
No. I have here mu and nu are x, y, and z.
Okay.
Let's look for a minute on u. That's easier. What is u? The small displacement from the lattice point. So at point r I have some displacement, and at point r prime I have some displacement, not necessarily the same displacement. Actually, if it's the same displacement in each point, it's not interesting because that's just the translation of the lattice. Nothing changed. No internal energy was gained by it. Okay, so I have three numbers for each lattice point in U, three numbers for each lattice point in point R prime. Okay? Now I'm asking what's the relation between them. So I should have here a matrix between points R and R prime. Why am I sure that it's R minus R prime and not dependent on R and R prime?
Symmetric.
Taylor extension.
Not symmetric, because each lattice point is symmetric. I can't have some other dependence between R and R prime and R and R. I translate both of them to two different points, it should be the same. Lattice is symmetric for translation. And I have a 3 by 3 matrix because I have directions x, y, z and directions x, y, z here. What else can it be? All of that we discussed in the previous lecture, and this is just a derivative of the potential, second derivative, do mu and do nu. Okay. And for my purpose, I don't really care what is the exact structure of this matrix.
Haven't we said it's diagonal?
No, it's not necessarily diagonal. I can diagonalize it. It's different. Especially for lattice structures that are not simple cubic or things like that. Things don't have to be diagonal, even. But what do I know? Just by construction, no matter how the potential field looks like, if I perform the derivative by mu prior to nu or vice versa, nothing changes.
That's the property of derivatives, isn't it?
Right. Or if I would like to be a bit more careful, actually I wrote as and therefore, if I want to be completely exact, can also write or okay, if I exchange R and R prime, nothing should change here. What else do I know? Someone has an idea for more resistance?
From moving around it.
Yes, but it has another ingredient in it. If I exchange mu with a constant, all of them moved by a constant. So I'm left with, I'm writing it here. Just why didn't I write here R and R prime?
What is the in this case?
Just a vector of 3 components. What does it mean? If I move each atom at each lattice point by a constant vector, what does it mean?
Nothing happens because
Nothing changes.
Nothing changes because I just move the whole
it
lattice.
doesn't depend on anything.
Doesn't depend on energy. And that's the, so these are the 3 components of the movement. They don't depend on R because they don't depend on R. That's the way I constructed it. And this summation should be equal 0 because it shouldn't contribute any energy. And that necessitates what's written here. Okay, so we know something about the properties of D, symmetries. What did we do in the previous case once we had U harmonic in order to find what waves exist in the system?
We guessed in a complex exponential.
Yes, but before that, we guessed as a solution to something. What?
Hamilton, the Schrödinger equation?
Okay, come on. We're not yet, we haven't yet performed any quantization. Exactly. Just we have to write down the motion equation. Nothing changed. Here the motion equation would be a bit more complicated, but it's still a motion equation. So, the good old motion equation. If you want a less intimidating name, F equal an A. Now we get to the point of guessing a solution and seeing if it actually fulfills this equation. Looks scary, but it's the same that we had previously. For each lattice point, we have an equation for the derivative of the displacement. The only thing that's added here, it could depend on each one of the direction x, y, z. Okay.
There isn't a minus before the summation?
I think there should be probably. So why is this solution? Analogous to what we did in 1D, the only difference is instead of having kx, we have now k vectors that has 3 components, and r is also a vector. And we can have a direction here for the plane of motion of this wave. I hope that for all of you it's somewhat reminiscent to what's happening in electromagnetic waves. The only difference is that here we don't have the special behavior of the polarization, which has to be perpendicular to k in electromagnetic waves. Here we don't have that condition. The equations are simpler and we have less constraints on the behavior of the wave. So epsilon at the moment can be in any direction. Okay. We still have periodic boundary conditions, which means that R okay. And therefore, reciprocal vectors and the conditions that reciprocal vectors have. Now, as a check that we understand what's going on here, does AI, does it have to be perpendicular, let's say A1 to A2?
No.
No. Does B1 have to be perpendicular to B2 or B3? No. Simple cubic, yes, but in any other complicated lattice that we have seen, BCC, FCC, etc., they are not orthogonal necessarily. They have to be orthogonal between them. B and A have to be orthogonal, but not
between themselves.
Not between themselves. So it's not that we define X, Y, Z by these relations. They could be anywhere. I did define that B is orthogonal to A, right?
But because B is a symmetric matrix, can't we define some orthogonal base?
And how do you call this procedure?
And unitarily diagonalize the matrix.
And that's what we're going to do. We'll get indeed 3 orthogonal directions, which are the modes of the system. What I'm pointing out, they don't have to be the same, or even for most of the lattices, they can't be the same as the directions of A or B. That's all. People tend to confuse the two definitions. Okay, so what will we do? Go back, just put in the solutions that we guessed and see if it fulfills the equation. Under what conditions? Meaning we'll get a dispersion relation and see what that teaches us. So I just wrote the left hand. I have a derivative, twice derivative on time, gives you the omega square, and put here minus. Okay, what do I get from the right hand side?
So E isn't a constant vector in this case? Or
It is, but it's a vector, so it has...
I thought it was a derivative.
No. So E is a constant vector. If it's not a constant vector,
It's
the
not
whole
smooth.
concept of modes is dead. So if you're doing a problem and ending up with an E that depends, so you know that simple mode decomposition of the system doesn't work. Could happen in nonlinear optics, it could happen in other situations, but then this is not a good way to proceed. I'll let you in on a secret, nothing is then a good way to proceed, so what do? Either you send your computer to figure it out, or you assume that you have still a small parameter and this change is relatively weak, and then you can somehow soldier on.
Perturbation theory?
Hmm?
That's perturbation theory?
That's some kind of perturbation theory. At the end of the day, what do we know to do in physics? Either we have well-behaved modes and then we can solve it completely, or we are approximating it with perturbation theory, or we are going to do numerics, or we have no idea at all what to do. Look what happens with string theory. We can write down the equation, we can't solve anything, we can't pull out any predictions, and we're stuck with a piece of, we can say it's beautiful equations, but we can't learn anything out of it. Or it's very, very, very hard to learn anything out of it. Okay, so let's write this part. Okay, here we just have to substitute u with the solution. Still looks like a mess. Well, I'll leave the left-hand side at the moment untouched and do some massaging of the right-hand side. Just continuing here because the blackboard is terminated. So what did I do here? I just pulled out e to the I minus omega t, which I'm allowed. Pulled out I to the power, sorry, e to the power ikr, and subtracted it from here because I pulled it out. I can't pull r prime because it's under the summation. Can at least get rid of this part. And because I sum over all the points I don't care if I'm starting at some R or another R, it doesn't matter. Therefore, I can replace R prime minus R by R prime. And according to the symmetries that we have shown a few minutes ago, can replace the minus by plus. We have shown that it's symmetric. And you should have screened on me because there's no minus omega t anymore because we pulled it out. So it seems no one here is conscious at this moment. And what do I have here? Just here. Summation of nu. An extension of a good old concept that you are familiar with, perhaps not in this form. E to the power ikr of some function r, summation of all. It's a Fourier transform. It's a Fourier transform of a matrix. Good. How do I Fourier transform a matrix? I Fourier transform each component. That's essentially what's written here. If you don't believe me, just write down explicit for mu and nu for each component and see. See where it looks. So I'll write down this, what I've got here and I'll return to it. And what does this mean? Just perform a Fourier transform on each one of the components of D. You have a 3 by 3 matrix. Why? Because mu and u are x, y, z. So I want to look a bit more carefully into this Fourier transform. So, by construction, okay. Meaning, choose x, y, take the xy component and perform the Fourier transform. Xz, Xx, whatever you feel like. So you have Fourier transform of the 9 different components of the mu. Okay. Now we'll use all the symmetries that we met previously. I didn't write it down just for my amusement. Somebody can tell me what did I do here? Okay, instead of writing I to the power kr, I wrote I to the power kr and minus and e to the power minus ikr and divided by 2. Why am I allowed to do it? Because d of r and d of minus r are the same. So I'm allowed to do it.
Y minus 2.
Y minus 2.
Because of the minus.
I'm doing it in order to get a nice function here. But why this is equal to 0? Because we have shown that summation over r of d mu n is 0.
So I could put in any constant.
I can have any constant. 2 is also a constant. So I used all my symmetries in order to write it down in this form. And what do I gain by it?
You can turn it into a cosine.
I can turn it into a cosine. Minus 1, and now I'll turn it into a sine squared. Reminds us very much the structure for the one-dimensional case. That was the reason to do all this exercise.
Because it's a Fourier transform, we can see from here that the k is going to be limited because it's periodic.
Actually, this we could have already known from here. It's periodic. It has to be. So I have here d mu n of k. It's 3 by 3. It's real and symmetric. How do I know it's real? This is real. Symmetric because mu nu can be exchanged. What do we know about a real and symmetric matrix?
You can diagonalize
I can diagonalize it and get 3 orthonormal vectors that span the whole space of solutions here. What they are? Okay, that depends very much on the exact structure of the mu nu. But for me at the moment, it's enough to know that I have 3 eigenvalues and 3 So basically, after diagonalization, I have lambda 1 of k, lambda 2 of k, lambda 3 of k, and all the rest would be 0. And in this basis, I'll have E1 of k So I can go back to my equations of motions. And instead of writing right, this is what we had previously. Call it S already in the diagonalized case. which is 3 times the one-dimensional case. The only thing that changes is that we have 3 branches, because S goes between 1 and 3. And each branch doesn't necessarily have the same speed, because it depends on lambda S over M, and lambda S doesn't have to be the same. Depends on the form of the interaction. How do I know that you have here a linear dependence on K? I go back and look what's happening here. For small k, I'm allowed to exchange it with simply k square here. And then I have omega square proportional to something times k squared, meaning I have an acoustic mode. So I end up with 3 acoustical modes. If I would, in some imaginary universe, have a 5-dimensional lattice, I'd have here 5 acoustical modes. So if I have p atoms, and this I'm not going to go through the whole calculation, just stated p atoms Okay, and what we're going to do in the next lecture, whenever that will occur, is that we'll see how this understanding helps us to understand the quantum heat capacity of the system. If you remember, we came out from the assumption that basically we have 6 degrees of freedom per atom. We have half kT for each degree of freedom. Therefore, we have 3 times nkt total energy for a given t, and derivative by t gives us 3kn. Now, without knowing anything about quantum mechanics, let's say if I have 2 atoms per lattice site, what do I know? I know that basically I have 2 branches. One of them starts with a finite value of omega. Right? I have the acoustical modes that can be as small as I want, but optical mode starts with some finite value of h bar times omega. We know that at low temperatures, these modes don't contribute. So without knowing anything, I know that it can't be 3 times n atoms contributing to the heat capacitance, because let's say if we have 2 atoms per unit site, half of them don't contribute at low temperatures. So already I see that from these simple or relatively simple considerations, I know something about the heat capacity, more than I would have known from just simple classical thermodynamics that tells me I have half kT from each degree of freedom. I know that part of my degrees of freedom don't participate at all, and the acoustical waves I'll have to treat a bit more carefully. Okay, and that we'll do in the next lecture.
Thank you very much.
Thank you.
Kind of, yes.